Our next test to tell whether or not a series converges or diverges is called the ratio test. Now this is probably the most useful test out of all of our tests, and it's a pretty simple test to do. Here's what it says. It says if we have the sum n equals 1 to infinity, let's say a sub n, if the limit as n goes to infinity, the absolute value of a sub n plus 1 over a sub n is less than 1, and then it converges. But since we're doing the absolute value of this, we can actually say it converges absolutely if the limit as n goes to infinity, the absolute value of a sub n plus 1 over a sub n is greater than 1, then it diverges. Now notice we have less than 1 means it converges, greater than 1 means it diverges. That's great. Not only does it tell it convergence, it tells us divergence. The problem is, and you might have guessed it, the one thing that we're missing, if we have a sub n plus 1 over a sub n, if it equals 1, this is called inconclusive, which means the test tells us absolutely nothing. Go try another test, basically. So the good news is this ends up being a pretty easy test to do. A little bit of algebra about it. So let's just say determine if it converges or diverges. Now in this case, if it does converge, we'll actually be able to say that it actually converges absolutely, and if it diverges, we say that it diverges. So I'm going to have to do a callback here real quick. If you are watching these videos in order, in the last video, I kind of jumped ahead a little bit on what we knew how to do. I asked us to tell whether or not this here converged or diverged. We really didn't have a test in place yet that can help us, but the ratio test will really help us out here. Now, here's the idea for when to use the ratio test. When you see lots of different types of functions, notice here I have an exponential and a factorial. You're thinking, you know what? Let me try the ratio test. It's pretty helpful here. So, here's what the test says. We want to do the limit as n goes to infinity, a sub n plus 1, so think about that as a function of n. So a sub n plus 1 would be 2n plus 1, n plus 1 factorial, all over a sub n, which is just 2 to the n over n factorial. And we want to know what that value is. We need to determine, is it less than 1, greater than 1, or actually equal to 1. All right, so we got a bunch of algebra here. First thing I'm going to do, limit as n goes to infinity. The absolute values. Notice everything inside there is positive, so we don't need the absolute values. So I get 2 to the n plus 1, n plus 1 factorial times, I'm just going to flip and multiply, n factorial over 2 to the n. Now what I suggest is rearrange these fractions so you have the same type of functions as ratios. Notice I have exponentials and exponentials, so I'm going to kind of line those up, and I have factorials and factorials. I want to line those up, so I'm going to do the limit as n goes to infinity. Let's do, doesn't matter which way, 2 to the n plus 1 over 2 to the n. I have n factorial over n plus 1 factorial. Now for each one of these fractions, simplify anything you can. For the limit as n goes to infinity, this is pretty straightforward, right? Because here we're just dividing, we have like basis, so it's the top exponent minus the bottom exponent. Or another way to think about it is I have one more 2 on the top, so we just have a 2. When we simplify factorials, you take the larger factorial, that'd be the n plus 1, and count it down till you get to the lower factorial, and then stop. And of course that will reduce, so I end up with the limit as n goes to infinity. The n factorials cancel, so I have 2 over n plus 1, which as n goes to infinity is 0. Okay, so which case are we in? So in this case, our limit is less than 1. So it's less than 1. So the sum n equals 1 to infinity, 2 to the n over n factorial converges. And the nice thing about this test, not only does it converge, it converges absolutely. All right, let's try another one, kind of like this one. Maybe we can interpret some results. So again, real quick, notice how dominating a factorial is. It completely got rid of that exponential, and we always think about exponential growth as being this super fast thing, but it destroyed that exponential so much that this thing actually adds up to a finite value. All right, let's try another one. It's going to be pretty close to this one, but let's see if we can make it diverge. What if I said the sum n equals 1 to infinity? Let's do another exponential over a factorial. Well, let's give the top some help and let's see if we can make it diverge. So let's give a power of n. Pick any power you want. How about, I don't know, the 20th power. So let's see if that helps, right? We're multiplying by a polynomial with a degree of 20, so that has to help this thing diverge. Now I'm thinking I want to do my my ratio test here because I have a mixture of a lot of different types of functions: polynomials, exponentials, and factorials. So let's see, we're going to do the limit as n goes to infinity. That's going to be n plus 1, 3 to the n plus 1, all over n plus 1 factorial, n to the 20th, 3 to the n over n factorial. All right, taking a look at our absolute values, everything inside here is positive, so the absolute values can just go away. And I'm just going to flip and multiply, so I get the limit as n goes to infinity. I get n plus 1 to the 20th, 3 to the n plus 1, all over n plus 1 factorial, n factorial, n to the 20th times 3 to the n. All right, all I did on that is flip and multiply. All right, just like before, I want to line up like functions because I got polynomials, exponentials, and factorials, so I want to kind of stack them on top of each other. So let's do limit as n goes to infinity. Let's do the polynomials first. I have n plus 1 to the 20th over n to the 20th times 3 to the n plus 1 over 3 to the n times n factorial over n plus 1 factorial. All right, kind of simplifying these, what are we going to end up with? We end up with the limit as n goes to infinity, n plus 1 to the 20th over n to the 20th. Again, we have one more 3 on the top, and I can rewrite this as n plus 1 times n factorial. So on that last one, the n factorials will cancel. Limit as n goes to infinity, n plus 1 to the 20th over n to the 20th times 3 times 1 over n plus 1. Okay, so remember, if we're doing the limit of a product, it's just the product of limits, so we can do the limit of each one of these guys. So if you want to write one more step here, I'm going to do the limit as n goes to infinity, n plus 1 to the 20th over n to the 20th times the limit as n goes to infinity of 3 times the limit as n goes to infinity of 1 over n plus 1. So that's what we're really doing here. You don't need to show this step. It's obvious that you're doing. All right, what's happening to this? Now, you can kind of multiply all this out and kind of get an idea of what's going to happen. Think about this. If you distribute that out, now you wouldn't want to, it'd be giant, but the first term would be n to the 20th, and then it'd be like 20 n to the 19th plus all the way down till you got to 1 all over n to the 20th. Now as n goes to infinity, this absolutely goes to infinity over infinity, and you can start doing L'Hopital's rule if you want to. But doesn't it make sense that all the lower powers would disappear when you do L'Hopital's rule, because we'd have to take the derivative, well, 20 times. If we did the derivative 20 times, we'd have the exact same number on the top and the bottom. So this whole piece right here is really just a 1 times the limit as n goes to infinity of 3 is 3, and the limit as n goes to infinity of 1 over n plus 1 is 0. So our answer here is 0. Now remember, we need to check now, that is less than 1, so this converges absolutely. So imagine that. That's how powerful a factorial is, how fast it grows. Because in this case, it not only dominated an exponential, it dominated an exponential times a polynomial. Now notice, I could have picked any power I want for this polynomial. That could have been the 200th power. The exact same thing would happen. It could be the 2 billionth power. The exact same thing's going to happen. So this factorial will outgrow any polynomial times any exponential. So pretty crazy how fast they grow. All right, let's try maybe one more of these so we can kind of see what can happen. All right, let's do one that maybe looks a little easier. What if I said sum n equals 1 to infinity m plus 2 over n squared plus 3. I'd say, okay, let's do our ratio test. I seem to like it. It's pretty easy to do. So we would say the limit as n goes to infinity, absolute value of, let's see, it's going to be m plus 1 plus 2 over m plus 1 squared plus 3 all over n plus 2, n plus 3. All right, again, in this case, since everything inside there is positive, we can get rid of the absolute values. Let's flip and multiply, so we get the limit as n goes to infinity. I'm going to get, I'm going to combine those like terms there. So that's going to be n plus 3 over n plus 1 squared plus 3 times n plus 3 over n plus 2. All right, what's going to happen here? Oh, look, that's n squared. Sorry, n squared. Okay, so what's going to happen here? Well, if you kind of think about this in terms of polynomial, we could distribute all this out on the top. And if we distribute it all out on the top, what's the highest power we're going to have on the top? We have an n squared times n. So on the top, we would have an n cubed. On the bottom, we'd have to distribute this out. This would give us an n squared times another n, which would be another n cubed. Now we're going to have a lot of lower stuff, plus lower stuff. But as n goes to infinity, that lower stuff really doesn't matter. So this limit right here, the limit as n goes to infinity, I'm just going to write it like this: n plus 3, n squared plus 3, n plus 1 squared plus 3 times n plus 2 is equal to 1. Now again, if you need to multiply all that out so you can see that happen, feel free to do it. But hopefully by now, if you finished the section on the limits, you're starting to notice how these patterns work. Well, unfortunately, 1 is our inconclusive case. Now, you can kind of see that might have given way, because remember I said one of the big keys when you want to do the ratio test is when you have different types of functions. Here all I have is polynomial and a polynomial, so this type of thing generally is going to happen. That doesn't mean that we can't figure this out, it just means that the ratio test won't work here. So we need to try another test. How about the limit comparison test? You don't hear that lawnmower outside? All right, so for the limit comparison test, remember here we have our a sub n is n plus 2 all over n squared plus 3. And as n goes to infinity, this starts to look like, well, the 2 and the 3 are going to go away. That's n over n squared. So what's the sum? N equals 1 to infinity of 1 over n. Well, that's a divergent p-series. With our p equaling 1. So we expect that this is also going to diverge. So let's do our limit comparison test. We need to do the limit as n goes to infinity of this divided by that. It doesn't matter which way you do it, remember? So it's going to be n plus 2, n squared plus 3 divided by 1 over n. Flip and multiply. Goes to infinity, n plus 2, n squared plus 3 times n, or n over 1. I'll move it up right here real quick so we get the limit. N goes to infinity. When we distribute on the top, n squared plus 2n, n squared plus 3 All right, so as the limit as n goes to infinity, again, the lower stuff kind of drops off. We get n over n, so this is 1. Now remember that 1 means something different now. According to our limit comparison test, if we get a number that falls between 0 and infinity, that means that these do the same thing. So, since the sum n equals 1 to infinity of 1 over n diverges, then the sum n equals 1 to infinity, what was it? N plus 2, n squared plus 3 also diverges. Okay, so you see all these tests are kind of going to wrap around together, but the ratio test is a great test to use, especially if you have mixed types of functions. If you do get a 1, try a different test.